Before I go through the overview of today's video, I wanted to comment that I was about to read this, and whenever I read this, I often say that it's a second order linear homogeneous differential equations. And when I say the word second order, I'm looking to see that there's a second derivative. I look at the y double prime, the y prime, and y, and see that it's linear. I look at the zeros, see that it's homogeneous, and I see that the coefficients are constant, and they're not functions like p of t and q of t. So I am going to suggest, because I must have said this 100 times, and now when I see this form, I automatically can pretty quickly say, oh, it's second order, it's linear, it's homogeneous, it's constant coefficients. And it just comes out because I've done that like 100 times. So I'm going to suggest that maybe you try that. When you see these generic forms, that you identify exactly what kind of differential equation it is, because that way it'll come faster to you, more natural to you, and you'll see lots of different forms of equations, and it's important you're able to identify what you're working with. Also, when you say this, it'll remind you as you go through this video exactly what we're looking at, because there's so many techniques that you've learned for so many types of equations. It's good to kind of cement in your head, oh, in this video we're talking about second order linear homogeneous differential equations with constant coefficients. And you look at this and those words should just come out. Anyway, so let's talk about what we're doing in this video. We're going to look at repeated roots. So in the previous video, we have shown when we solve this second order linear homogeneous differential equations with constant coefficients, when the roots of the characteristic equation, which looks like ar squared plus br plus c, and again, these coefficients are exactly the coefficients of your differential equation. So we have this characteristics, and when the roots are real and different, or are complex conjugates, we've seen in previous videos how to handle that. In this video, we are going to consider the third possibility, namely that the two roots, r1 and r2, are equal to the same thing. In other words, they are going to be equal to negative b over 2 over a. And then we'll have one single solution. y1 is equal to e to the negative bt divided by 2a. And so now we'll find, how do we find a second solution? And that way we can have a fundamental set of solutions. So first we will look at repeated roots, and what I have here is actually what we're going to find the solution. Our first root is going to be our e to the minus bt over 2a. Our second root is simply going to be t times e to the minus bt over 2a, but we will develop this equation for during this video, and here we have the general solution. We will do this as well as other examples, and then we'll cover reduction of order. And the idea of reduction of order is the same procedure that we kind of use to get this second solution, which we haven't discussed yet, can be used in a more general setting. In other words, when we have a second order, linear, homogeneous differential equation, but now the coefficients do not have to be constant, we can use a very similar technique here if we have a solution with just one, if we only know one solution, how we can get a second solution. And this technique is known as reduction of order for reasons that we'll get into when we do our examples. This second overview is sort of a bonus slide. It talks about the characteristic equation for this second order linear homogeneous differential equation with constant coefficients. What happens when we look at the characteristic equation and the roots are real but not equal, that this is our general solution. When the roots are complex conjugates, then this is what the general solution looks like. And in this video, we're going to cover when the roots are equal, then this is what the general solution looks like. So it's your bonus kind of summary slide. We're going to start with an example. We're going to solve the differential equation y double prime plus 4y prime plus 4y equals 0. We assume a solution of the form y equals e to the rt, and then we take y prime and y double prime, we factor out the e to the rt, and we realize this characteristic equation, which is equal to r squared 4r plus 4, and again, it's kind of easy to get it directly off of here since the coefficients of this differential equation becomes your coefficients in your characteristic equation. Here's your 1, here's your 4, here's your 4, which is equal to r plus 2 squared, and that characteristic equation now equals 0. So what that tells us is r is equal to minus 2. So y1 is equal to e to the minus 2t. So we have one solution, but to find a fundamental set, we need a second one. And we're going to use a technique, the D'Alembert method. And what that says is, well, if y1 is equal to e to the minus 2t, then we know any constant multiplier times e to the minus 2t, any constant multiple of our first solution is also a solution. So the idea is, well, what if we consider y equals then a function of t times y1? In other words, v of t e to the minus 2t. Is there a time where we can say that this v of t e to the minus 2t also a solution of the equation? So actually that was a question. So the problem becomes, when is this equation a solution to this differential equation that we were given? And what we do to answer this question is plug it in. So we're going to look at y2 prime, which is using the product rule, v prime of t e to the minus 2t, minus 2t, v of t e to the minus 2t. Yeah, the derivative of minus 2t is just minus 2. Then we find the second derivative, again making sure we use the product rule, and we get v double prime e to the minus 2t minus 4v prime e to the minus 2t plus 4v e to the minus 2t. Next, I rewrote my differential equation. I just transferred it from here to here, and I plug in my y double prime, my y prime, and my y into this differential equation. And I did factor out the e to the minus 2t, since everything seems to have that term in it. You know, here's my y prime, everything has this e to the minus 2t. So I factored it out, but when I multiply this, here I have my y double prime, multiplying by e to the minus 2t, I have my y prime, multiplying e to the minus 2t, and I have my y. And again, for the differential equation, all of that is equal to 0. And when I look at this, a bunch of this cancels out. My v prime, there's a minus 4 and then a plus 4v prime. Looking at my vt's, here I have 4, so I have 8vt, which cancels with this vt. So what I'm left with is v double prime of t is equal to 0, because e to the minus 2t is never equal to 0. So when you have two things multiplied together equal to 0, one of the factors has to equal to 0. So v double prime must equal to 0, which means v prime of t must equal to some constant, which means v of t must equal to some constant times t plus another constant, right? Just integrating here, I get a constant. Integrating here, I get c1t plus another constant. That means my y2 solution, which is v of t e to the minus 2t, is equal to e to the minus 2t times, and here we have v of t, c1t plus c2. So this is my y2 of t, my e to the minus 2t, c1t plus c2. And just multiplying this out, I get c1t times e to the minus 2t plus c2 e to the minus 2t. So this part here was my original equation, y1. And now this part here is my new solution. And last, here is my new general solution. And to verify that this is indeed a general solution, I take the Wronskian. So I have my y1 t e to the minus 2t, y2 e to the minus 2t. This is my y1 prime, this is my y2 prime, and I get e to the minus 4t, which is not equal to 0 for any value, which means that y1t e to the minus 2t and y2 e to the minus 2t is a fundamental set of solutions. Now that we have solved this for this particular equation, we're going to solve it for the general equation. Here is our general equation. A y double prime plus b y prime plus c y equals 0. Again, it is a second order, linear, homogeneous differential equation with constant coefficients. The characteristic equation using the same coefficients for our characteristic equation, ar squared plus br plus c equals 0. And we're going to assume that b squared minus 4ac equals 0. And this is exactly when we have the two roots are equal. we're going to use the same method that we used in the last example. To find our second solution, or to find y, our general solution actually, we're going to let that equal to some function of t, we'll call it v of t, times our first solution, y1. So that's v of t times e to the minus bt all over 2a. We calculate y prime, and we calculate y double prime, remembering to use the product rule. And then we plug our y here, our y prime, and our y double prime into the equation. So we have a times y double prime plus b times y prime plus c times y. All of these, oh, and I did factor out my e to the minus bt over 2a again, is equal to 0. And then I can group everything, all my v double prime terms, there's only one that's multiplied by a. I group all my v prime terms, there's this one here, and there's this one here. And you'll also notice that they cancel out. And then I group my v of t terms, that's this one here, and this one here. And there's one more, this one here, v of t here. So there's 3 of them. Also, if you've done all this, your derivatives correctly, this v prime of t will always cancel and go away to 0. And it also turns out that this last term should cancel and go away to 0. Remember last time we just had a double prime was equal to 0. And I have the cancellation here, I have it kind of worked out in blue here. And it does depend on this last part canceling, depends on the fact that b squared minus 4ac equals 0, which is exactly how you got r1 equal to r2. And once you have everything canceling out, you have a times v double prime equals 0. Well, a is not equal to 0 because otherwise you'd have a first order linear equation. So it must be v double prime is equal to 0. Again, if you integrate, then that means v prime of t is equal to c1, and v of t is equal to c1 plus c2 times t. So our general equation is going to be c1 e to the minus b over 2a. That's our first solution that we had before, plus our new solution. Oh, and actually it's also the one that we get for multiplying c times, well, anyway, and our next solution is going to be c2t e to the minus bt over 2a, because this is v of t, but remember our solution y is equal to vt times our first solution. So here is our general solution. Again, I can calculate the Wronskian, which is never equal to 0, so I do know that this is in fact a general solution. And this is it. In general, once you have one, no pun intended, once you have one solution, to get the second solution, all you need to do is multiply your first solution by t. We will do another example. So we have y double prime minus y prime plus y over 4 equals 0, and it's an initial value problem. Y of 0 is equal to 2. Y prime of 0 is equal to 1/3. So looking at this, we get our characteristic equation, taking the coefficients from our differential equation. We have r squared minus r plus 1/4, which is equal to r minus 1/2 squared, is equal to 0. That means r is equal to 1/2, and our first solution is equal to e to the 1/2 t. So we can just right away, so we could do all the work that we did in the last problem, and maybe it's a good thing for you to just go through the steps so that you remember what we did. We essentially said, what if we multiply y1 times a function of t, and we called it v of t? And then we took the derivatives, we plugged it into the equation. But essentially what you're going to get, if you recall, our general solution is just going to be our first solution times a constant plus our first solution times t with a constant as well. This is an initial value problem, so we have to use our initial values. Y of 0 is equal to 2, that's our first initial value. So that's equal to, plugging in t equals 0 here, I get c1, and then t is 0 here, so it's plus 0. So c1 is equal to 2. Then y prime of 0 is equal to 1/3. That's our second equation for the initial values. So I have to calculate y prime, so I do that, making sure I use the product rule here. I plug in 0, and I get 1/2. Is that right? Yes, I get 1/2 c1. This is plus c2, and here I get 0. So what I get is C2 is equal to minus 2/3. So my general equation is going to be here. I have C1, which is, where did my C1 go? It's somewhere here, is equal to 2 times e to the t over 2. And that just happens to be what our first solution was, plus C2, which is minus 2/3 times t e to the t over 2. So this is my solution to the initial value problem. Which brings us to this summary slide for second order, linear, homogeneous differential equations with constant coefficients. We solve that by looking at the characteristic equations. Now, if the roots are real and not equal, then this is what the general solution looks like. C1e to the R1t plus C2e to the R2t. If R1 and R2 are complex conjugates, in other words, the roots is equal to this lambda plus or minus I mu, then the general solution, y, is equal to C1e to the lambda t cosine mu of t plus C2e to the lambda t sine of mu of t. Now, if R1 equals R2, and we'll just say that's equal to R then, that's what we've been talking about in this video, then the general solution is C1 e to the RT plus C2t e to the RT. And that brings us to our next topic, reduction of order. The idea is if we know one solution to this second order linear homogeneous differential equation that has p of t and q of t functions of t for coefficients, how can we find a second solution? So again, it's similar to what we were doing in that we have one solution and we need a second solution, but we're going to apply this to a more general case. We're no longer demanding that the coefficients of y prime and y be constants. So to find a second solution, we're going to use the same approach. We're going to let y equal some function of t times our first solution, y1 of t. Then we take the derivative, y prime is equal to this using the product rule, and y double prime is equal to this using the product rule again. We plug it into our equation. Again, it's our y double prime plus p of t, y prime plus q of t, y equals 0. And we get this equation here. I have rewritten this equation right here, my y1 v double prime, my 2y1 prime plus p of y1 times v prime, my y1 double prime plus py1 plus qy1 times v equals 0. And what you'll notice is this y double prime plus py1 plus qy1, that's exactly the differential equation we were trying to solve. Which means since y1 is a solution and this has y1 in there, this part goes to 0. Remember, y1 is a solution to this differential equation, and by this right here, not the v, but what's inside the parentheses is equal to 0. What we are left with is y1 v double prime plus 2y1 plus py times v prime equals 0, which is a first order differential equation. But wait, you say it's not a first order because there's clearly a second order derivative here. And we'll get to it. So actually, you're right, this is not a first order differential equation, but it can be made into one by simply substituting w is equal to v prime. And we will do the details of that in just a moment, but I'm just going to pause to say this procedure is called the method of reduction of order because the crucial step is the solution of a first order differential equation. We're going to convert this to a first order differential equation for v prime rather than the original second order differential equation for y. So we are given one solution, y1 is equal to t to the minus 1, for this differential equation, 2t squared y double prime plus 3t y prime minus y equals 0 for t greater than 0. And we want to find a fundamental set of solutions. In other words, we need another solution to this equation. You will notice now we have a second order linear differential equation, homogeneous differential equation, but now you can see that we no longer have constant coefficients. We have functions of t in front of our y double prime and y prime. But nevertheless, we're going to use that same approach that we did for repeated roots. In other words, we're going to let y equal a function of t, which we will call v of t, times our first solution, t to the minus 1. We'll take the derivative of y, and then we'll take the second derivative. I plug in my y prime, and my y double prime into my differential equation. So I have 2t squared y double prime plus 3t y prime minus y. And now I group my terms that are multiplied by y double prime, and I only have one. When I multiply this, I get 2, and then my t squared times t to the minus 1 gives me t v double prime. Next, I'm going to look for what multiplies v prime. Here I have my minus 2 times t to the negative 2, but I'm going to multiply that times 2t squared, and that's going to leave me with minus 4. I also have a v prime here, so I have a 3 times t to the negative 1. That will just leave me 3 times v prime. And then at the very end, I am going to look for the terms that is multiplied by v. So I have this one here, so I have my 4, and then my t squared and t to the minus 3 is going to give me 4t to the minus 1. Over here I have 3t times t to the minus 2, which will give me, and there's a minus here, minus 3t to the minus 1, and then finally I have minus t1 v. Here you can see my 4t to the negative 1 is going to cancel with this minus 3 and this minus 1t to the negative 1. So what I'm left with is 2t v double prime. Here I have minus v prime equals 0. You know, looking at this equation, it must be like an e because, you know, double prime, if I move this over, equals single prime, and, you know, e appears everywhere. But actually, that's actually not really the point. When we continue, I had made the claim that this form here was going to be a first order differential equation. So how did I make that work? I told you we were going to do a substitution of variables. In particular, we are going to let w equal v prime. So now this equation is going to become 2t w prime minus w equals 0, which is clearly linear. We know how to solve first order linear equations because we remember what we did a few weeks ago. And if we don't, we're going to review it. Okay, so we divide the whole equation by 2t so that we can get the form where the w prime doesn't have a coefficient. Well, it has 1 as a coefficient. And then over here, then, if we divide by 2t, the coefficient in front of w is minus 2t, 1 over 2t. W equals 0. To solve this linear equation, we're going to use an integrating factor, which is equal to mu equals exp of this function in front of w, which is minus 1/2 over, or minus 1 over 2t dt, which is equal to, if I integrate this, I'm going to have a minus 1/2 natural log of t. So e to the natural log of t to the 1/2, which is equal to t to the 1/2. So now I can multiply my equation here by my integrating factor. I have, I multiply this equation by my integrating factor, and I get 2t times t to the minus 1/2 w prime minus w t to the minus 1/2 equals 0. I integrate both sides of the equation, but I remember that the point of the integrating factor is this whole side, this left-hand side of the integral, is my integrating factor times w, and that's equal to integrating 0. I get a constant. So w is equal to c t to the 1/2. And I, was all excited about getting the solution. I even underlined it, but then I remembered, wait a minute, no. W is equal to v prime, so we need v prime. So integrating this to get v, I get c t to the 1/2. So I'm going to have 2/3 t to the 3/2 plus k, a constant. And now, we're still not quite done. Now that I have v, I want to get y by multiplying v times t to the minus 1. So I have y is equal to, here I have my v, which is 2/3, 3/2, and I just renamed my constant c1, times t to the minus 1. Multiplying this, I get my 2/3 t to the 1/2 plus times some constant, C2, and then I have my C1 times t to the minus 1. I can calculate my Wronskian and see that it is not equal to 0 when t is greater than 0, which is what is given to me in the problem statement, and therefore this y1 t to the minus 1 and this y2 2/3 t to the 1/2 are my fundamental set of solutions. To review what we covered in this video, we considered the second order linear homogeneous differential equation with constant coefficients. We solve this by assuming our solution is of the form y equals e to the rt. And then we got this characteristic equation, and we had three different possibilities. Either the solution had two real roots, or it had two imaginary roots, or it had two roots that were equal. R1 is equal to R2, which would be, when you solve it, it is equal to negative b over 2a. So then we can get one solution, y equals e to the, again, rt, which is negative bt over 2a. But now we want a second solution so we could come up with a general solution. And so this technique was of repeated roots. Again, y1 is equal to e to the rt, and in this case the root is equal to negative b over 2a times t. And then what we found is y2 is simply t times e to the rt, or t to the e to the minus b over 2a times t. And then our general solution was c1 e to the rt plus c2 t e to the rt, and rewritten with the root here. We used this example to outline our approach. What we did is we said if y1 is equal to e to the minus 2t, and we also know that any constant multiple of y1, in other words, c e to the minus 2t is a solution, what if we took a function of t and multiplied it by y1? Could that still be a solution? To answer that question, I calculated y prime of, that is the derivative of v of t e to the minus 2t, and then I calculated y double prime. And then I plugged it into my differential equation, y double prime plus 4y prime plus 4y equals 0. And here I have it written out, my y prime, y double prime, y prime, and y. And I had factored out my e to the minus 2t since it multiplies everything. And it equals 0. And what I found after some algebraic manipulation is v double prime of t is equal to 0, which meant v prime of t is equal to c, right, if you integrate, which meant that v of t is equal to c1t plus c2. So this is v of t. And remember that y is equal to v of t times e to the minus 2t. So I multiplied this out by e to the minus 2t, and I get y1 is equal to c1t to the e to the minus 2t plus c2 times e to the minus 2t. And then I calculated my Wronskian just to confirm that I did have a fundamental set of solutions and I did have a general solution. So here I have my original y, and my y2 is simply t times my y1. And that's exactly what I have summarized here. y1 is equal to e to the rt, and y2 is equal to t times e to the rt. The next thing we looked at was reduction of order. In particular, we looked at a second order linear homogeneous differential equation, but now we relaxed the condition that we had to have constant coefficients. Now we allow functions of t in front of y prime and a function of t in front of y. We used the same approach where we said if we have one solution, or well, I should actually tell you what the problem was. It was, suppose we know one solution and then of this differential equation, and we want to find a second solution. So we used the same approach. We said, well, let's look at y equals a function of t times our first solution. We took the derivatives, we plugged into our equation, we found that these other this solution here, which did not look linear until we let w equals v prime, and we got a linear equation, and then we solved the linear equation, and then, yeah, we basically solved the problem and found the second solution. And this procedure is called the method of reduction of order because the crucial step is the solution of a first-order differential equation, this one here, for v prime, rather than the original second-order differential equation. And this was our example here. And we also had this bonus second overview slide, which was to go over the second order. Remember, you should think about the second order because it only has a second order derivative. Linear, it looks linear. Homogeneous, the zero. Differential equation with constant coefficients. So we solved that by looking at the characteristic equation. For the characteristic equation, there are three possibilities. Either the two roots are real but not equal, and this is what the general solution looks like. It is y equals c1e to the r1 of t plus c2e to the r2 times t. If r1 and r2 are complex conjugates, that is lambda plus or minus I times mu, then the general solution is y equals c1e to the lambda t times cosine mu of t plus c2e to the lambda t times sine mu of t. And finally, what we covered in this video, if r1 is equal to r2, so we'll just say it's equal to r, then the general solution is y is equal to c1e to the rt plus c2t times e to the rt. So that's it for this video. Thank you for watching.